This is regarding inscribed angles and circles. First off, let's remember what inscribed angle means. We had it previously when we talked about triangles. It means that the vertex is on the circle. When it was a triangle or other ones, it meant that all of the vertices would be on the circle. So we're going to start here with a circle and with an angle that's not in it. Then we're going to move the angle over and see what happens. Okay, so here I go. I want to see what the arc is that the angle captures or intercepts or subtends. So I pull it on a little bit. The angle is capturing, intercepting, subtending this little arc here. Not very big. I push it in some more. Arc's bigger. Push it in some more, and up I get to the center. And we recall that this is the definition of the measure of the arc, is the central angle. So when the vertex is at the central angle, then the measure of the central angle is the measure of the arc. Okay, so I'm going to push it some more. It's halfway across the circle now. I came in, I'm going, oops, halfway across. I've gone that far. Now I'm going to go some more. Notice that the angle, say it's about 50 degrees. This 50-degree angle is still 50 degrees. There's 50 degrees over here, it's 50 degrees over here. It's always 50 degrees, but look with the arc. The arc is not always 50 degrees. It's 50 degrees when it's exactly at the center. That's now a 50-degree arc that's intercepted by the angle, and it's a 50-degree angle at the center. Before it was there, it wasn't so big. It wasn't 50. Because, a reminder, the arc is always measured relative to the central angle. Excuse me. So even though that angle there is a 50-degree angle, that's not how we measure it. We talk about what it is from the center, the central angle. So whatever that is, maybe 10 or 15 degrees, is actually the measure of this arc and not the green one that's captured by the green side. Okay, so there we are. Small arc, bigger, bigger, bigger. Exactly 50-degree measure of the arc. Bigger, 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 but the angle's still 50. Bigger, 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 bigger. Oh, there we go. Now the angle is inscribed. The vertex is in the circle. Well, let's kind of look at that. I have here also two handy-dandy 50-degree angles that happen to be orange. I'm going to place them how we measure it by default, which is at the center. So now the central angle there, and the other one from this place. And we'll notice it's two, 50 degrees, central angle. This is a 50-degree arc. This is a 50-degree arc. Therefore, the arc is, by arc addition, some of the parts is the whole, the arc is 100 degrees. But wait! The green angle is still a mere 50 degrees. That's interesting. That's a 100-degree arc. That's 50. That's twice as much. Oh, wait, the angle is twice as far away from entering the circle as it was. Okay, so what can we see here? We can see that when the angle is inscribed, the arc that it subtends, that it intercepts, is twice the value of it. Or, in the other way, the value of the measure of the arc is twice the angle, or the angle is half the arc, either direction. And that happens to be a theorem. Please make note of the theorem in your cipher. Okay, let's look at this one and say, okay, well, this angle here at E, this blue angle here at E, is half of the arc DF. Okay, well, what happens if I just make myself a random other angle over here? So then this is going to be the angle, an angle that also opens to the arc DF. So what can I say about the blue angle and the orange angle? Well, they both open to the same arc. They intercept the same arc. The blue angle is half of the measure of the arc. The orange angle is half of the measure of the arc. Oh my! Half of the same thing means equal to each other. A little bit of transitive property going on here. So we have a little bit of transitive property going on here. So this angle opens to the same place that this angle opens. There we go. There we go. Therefore, they're equal to each other. Here's a circle. I'm going to make a diameter. Then I'm going to put an angle in. Let's look what happens here. Put an angle in that opens to this diameter. Okay. It's a diameter. It cuts the circle into two equal halves. This is a semicircle. It's 180 degrees. This angle intercepts a 180-degree arc, which means half of 180 is 90. This is a right angle. This should look familiar. This is very much like the circumcenter theorem that we did when we did triangles. You'll recall when we did the circumcenter theorem that when you construct the circumcenter, which is the concurrency of perpendicular bisectors, if you have an acute angle at the back, then the circumcenter will be inside the triangle. If it's an obtuse, it'll be outside the triangle. And if it's right, it'll be on the hypotenuse. We used that and we drew circles around it. If you look back at your notes, we pasted in some little triangles where you constructed each one of these. That was from the perspective of talking about triangles. Now we're doing the same thing with the perspective of talking about circles. So when an angle intercepts a semicircle, the angle is always 90 degrees. Now this is going to be something that you're going to do in some other math courses after here. Notice that any place that this angle is, no matter how close or how far from the diameter, the result is always a right angle. What if I have a little bitty distance here? It's still a right angle. Doesn't matter where you put it, it opens to a diameter. It is a right angle wherever you put it. It is an inscribed right angle. And here's the theorem with regard to that and its converse. Oops. There we go. Other things can be inscribed. Some of the other things that can be inscribed. Well, first off, remember the circumcenter theorem tells us that all triangles can be inscribed in the circle. When we dealt with the apothem and measurement, we found that all regular polygons can be inscribed in a circle, and that there are other various ones that can, but it's not always reliable. Since we use a lot of quadrilaterals, let's look at what quadrilaterals can be inscribed into a circle. Let's kind of look at what we've got here. Here's some of them. A square is a regular polygon, so obviously it can be inscribed. A rectangle is not regular, but all rectangles can be inscribed. I think you can see as it gets skinnier, it would come into here. As it gets fatter, it would come up into here, and it would still be inscribable. This, excuse me, trapezoid is inscribed, but all trapezoids cannot be inscribed. This particular type can, which I hope you'll recognize is an isosceles trapezoid. Here we have two kites. One can be inscribed and the other cannot. Okay, look at the things that are inscribed and see if you can see the commonality. it might help to remember one of our theorems about isosceles trapezoids, and that is that the opposite angles are supplementary. The opposite angles are supplementary. Well, is that true of a square? Yeah, it is. They're all 90. They're supplementary. Is it true of a rectangle? Yeah, it is. They're all 90. So that might be our common thing to look at here. Let's look at the the kite that works and see if we can figure out why it works. You might recall that a kite is symmetrical about its long axis. It wouldn't fly as a kite if it were not. Okay. So you'd have here symmetrical. I've drawn the axis of the kite, but notice a diagonal of the kite. But notice in the circle, what is that? It's the, it's the diameter. Oh, and look, the two sides of the kite angles open to the diameter. That's a right angle. That's a right angle. A kite that can be inscribed has right angles for its left and right in the usual configuration. Its left and right vertices will be right angles. Why? Well, it's symmetrical, or it wouldn't fly, it wouldn't be a kite. And if we're asking when it can be inscribed, then that angle has to open to the middle, which is 180 degrees, has to be half of 180 degrees, which is 90. So that has to be a 90-degree angle. In the kite, these two are congruent, the left and right, and the top and bottom are not congruent. So right angle, right angle. You recall in a kite that the other two are never the same. So this one's too big and that one's too small, but together they add to 180. So are all of them supplementary? Yes, they are. That's the commonality with regard to all the quadrilaterals that can be inscribed. Here's the inscribed quadrilaterals theorem, which we just demonstrated, and that is that to be able to be inscribed, the opposite angles have to be supplementary. That's both ways. A quadrilateral can be inscribed if and only if the opposite angles are supplementary. Let's look at a few problems. We have here asking what is the inscribed, the measure of angle A which is inscribed. We notice that it's not the central angle. We're coming in. The central angle would be right there. If it were the central angle, it would be 84 degrees, but it's not. It's pulled back twice as far, so it's half as much. The measure of angle A is 42. Look at this one. What's the indicated measure? Again, it's twice as far from the edge. It'll be half as much as the arc. But what's the arc? Well, do 360 minus 70 minus 120. You'll get 140. So, the measure of the angle is 70 degrees. In this one, a recall on our defaults for diagrams. If you have a line with a dot and it's at the center of the circle, then that means that the line, in this case LN, is a diameter. That it's a diameter means that it cuts it into semicircles. The arc here from L to N, L to N is 180 degrees, minus M to N, which is the arc MN, which is 160 degrees, so there's 20 degrees left there. But the angle is half because it's twice as far away, so the angle N is 10. Here are a few other problems that you can work, and I'll put the answers up here in a minute. So, pause it. Here are the answers, just to make sure you've got them right. Here's some more problems. Let's look at this one. The question is, name a pair of congruent angles. Remember the transitive of the inscribed angles Notice that angle D opens to arc AB, and that angle C also opens to arc AB, which means that C and D are congruent. Doing it backwards the other way, A and B in this case are also congruent. This problem. Recall that the opposite angles of an inscribed quadrilateral are supplementary. This quadrilateral is inscribed, so that means that x plus 80 is 180, so x must be 100. Y plus 95 is 180, so y must be 85. Here are some other problems that you can work on this to make sure you know what you're doing. Pause it if you'd like, and I'll put the answers up. And here are the answers. And here ended the lesson.